Greetings, here we go. We're going to talk about something called geometric sequences. So geometric sequences, well, they're very similar to arithmetic things as far as, well, there's a starting value. What would we call that? A1. And then, of course, you're going to see that there is a definite pattern to these guys. Look at the pattern I'm generating. What do you think the next number is supposed to be? If you guess the next number should be negative 24, then you're correct. Because what I'm generating here is a sequence of numbers that has what's called a common ratio. A common ratio. So since we already spent a lot of time talking about arithmetic sequences, and you don't have to relearn how to write stuff out, this should go pretty easy. So here we go. If I can visibly see the pattern, it's pretty easy in this one. I'm multiplying by 2 each time. That number is called the common ratio. And we abbreviate that. We call it R. Well, in this case, R equals 2. Now, the thing is, sometimes it's not real easy to see it right off the bat. And if that happens, it's very similar to our arithmetic rule. When the arithmetic stuff, when you're looking for the common difference, and then they give you something weird like decimals or fractions, well, here's the rule for this. If I take any number in the list, I'm going to take negative 24. If I take any number and I divide by the number that came right before it, I get a number. If I take any number in the list and I divide by the number that came right before it, and I keep getting the same number no matter what number I grab, if I divide by the one, there we go. That is why it's a number that is in common, and since we find it by doing division, we call it a ratio, so it's a common ratio. Abbreviated, we call it R. So guess what? If I asked you, what is the first term in this sequence? You already know the vocab. You know how we talk about these things. So you would say, hey, that's the first term. And then I'd say, hey, what do we abbreviate? How do we call it? And you'd say, A1. Now here's the thing. That is exactly how we would do it. But just like with arithmetic stuff, we have 3 ways to describe one of these things. But we don't have to go through all the stuff we did before. Let's just pick up where we left off. One of the ways to describe a sequence is with a recursive definition. So, for geometric things, it's very similar. Here is our format. We say A1 equals whatever the first number is. So we say A1 equals first term. And then, if you want to know any number in the list, you take the one that came before it, and this time, instead of saying plus D, we say times R. That's what makes it a geometric sequence. You multiply by the common ratio. And this, of course, is just like it was before. This is the format we use to write a recursive definition for someone. So for our problem up above, for our question up above, we would just say, oh, I could fill in this format, A1 equals negative 3, because that was the first number in the list. If I want to know any other number, I got to know the one that came before it times 2. That would be a successfully written recursive definition because I followed the correct format. This is our format for this stuff. Flashcards. Flashcards. That was a hint. For this guy right here. So one way to describe a sequence is to list the terms, write a list. One way to describe it is to write a recursive definition. That would be the recursive definition. And then, here's the nice thing about geometric stuff. When you write a rule for a geometric thing, the nth, okay, once again, they can call it an nth term. They can call it an nth term definition. Or they can call it a rule or a rule writing formula. So what do? We say, oh, a sub n equals a1 times r to the n minus 1. That is our formula. So if you want to write a rule describing a geometric, not an arithmetic, geometric sequence, you just do this. It's very simple. You go, I'll write the rule. I would say a sub n equals, well, in my case, it was a1 times r to the n minus 1. That's it. That's the whole shebang. So let's suppose they say, hey, you got this way to describe it, that's one of them, write a rule. You got this way to describe it, that's two, that's recursive definition. And this way, by listing the pieces out, that's the third way to do it. Now, with geometric stuff, though, the rule, you don't have to do any cleanup. You don't have to condense terms or combine stuff. So it's fast, it's quick. But here's the dealio with this. If I want to find out, like, what is the 8th number in the list? I want to know what the 8th number is. Well, that means n would be 8. So it would look like this. Negative 3 times 2 to the n minus 1. So what does this look like when I make it pretty? Negative 3 times 2 to the 7th. See, whatever number, I want to find the 8th term in this list. Here's the part, I'm just trying to point this out. People blow this all the time. This answer right here, this number right here, is always going to be one smaller than where you're at. So you want to know the 8th number? N minus 1. 8 minus 1, it's going to be 7. If this was, I want to know the 18th number, then it would be n minus 1. This would be a 17. Okay? Just so you know, I'm going to go back to what it was. And then, hey, I'm just going to grab my calculator and say negative 3 times 2. But I'm going to be careful. I'll put the 2 in parentheses, and I can knock it out, and I get my calculator to help me out, and it says the answer is negative 384. Now, here's something I want you to kind of think about, because it's going to affect us when we start playing with more complicated things. But the 8th number in the list, look at this. Let's see. Look at our list. This is only 4 numbers. By the time I get out just to the 8th number in this list, by the time I get there, we're at negative 384. So what I want you to kind of realize about things that are arithmetic, you get from one term to the next by adding. This is done by multiplying. So, I mean, if you punch in something like, what is the 18th number in the list, you know, you're only 18 numbers from the start of the list, and you are already going to be blowing up this calculator. This is, what is that? Negative 393,216. That's only 18 numbers away from the start. So geometric stuff can get really big really quick, or it can get really tiny real quick. Really tiny real quick. What do you mean by real tiny? Well, I mean something like this. What if they gave me a list of terms and they said, hey, we got this list of terms and we're going to do this. And they're going to say, here is a geometric sequence. Write the recursive definition, write the rule, and, I don't know, find what the 10th number in the list is. So what do? I go, well, I don't know exactly what the R value is. You might look at it and go, oh, I totally know it's 1/3. R has got to be 1/3. Okay, well, here's the thing. Take any number in the list, divide by the one that came before it. Take any number in the list, divide by the one that came before it. So if you're unsure, because sometimes they are sneaky, they're hard to figure out what it is. If you're unsure, write it out like that. And then remember, if you want to, hey, this is just something I could punch in on my calculator, or I could say 2/3 times the reciprocal, because I would just flippy flop that guy, and then bam, there it is, bam. Or this, you could say 2 divided by 6, well, that's just 2/6, which reduces to 1. Oh, it is a common, what is it called? A common ratio. So what's the R value in this thing? R is 1/3. So I go, hey, there's A1. R is 1/3. I could easily construct a recursive definition. How do I do it? I say A1 equals whatever they give me first term. A sub n equals A sub n minus 1 times R. There's my recursive definition. What about the rule? Okay, well, the rule would be A sub n equals A1 times R to the n minus 1. There's my rule. And here comes a rule for you guys. In this section, if I give you regular old numbers, you can give me back whatever you want. Regular old numbers. Hey, this turned out to be a decimal. Do I have to write it as a fraction? No. But here's the supreme rule. If I give you fractions in the original problem, then I want you to work with fractions. So as you can see right here, there's a 2/3. That's a fraction in the original problem. So I want to look at your work and see everything that could be fractional is expressed that way. Therefore, when you find the 10th number in the list, I want to find out what the 10th number in the list is. I do not want it written as a decimal. I want it written as a fraction. So let's look at that. So I'm going to go 6 times 1/3 to the 9th. Don't put a 10 there. Don't be tempted. Don't be putting no 10 there. And then what I'm going to do is I'm going to go 6 times 1 divided by 3, so 1/3, to the power of 9. And I hit my calculator button, and I get this really weird E number. What the heck is going on in the universe? I get this, 3.04, and it keeps going, and then it says, oh, get that out of the way. Then it says E negative 4. Now, we've seen this when we were doing stuff with our graphing calculator when we were looking for zeros of a polynomial. The calculator sometimes did this. So what I want you to do, I want you to see what I'm talking about. So if you have not punched this into your calculator yet, try it. Because some calculators, like the older TI-83s, will get locked up. I have my TI-84. I'm going to try it on the 84 and see what happens. So once again, it was 6 times 1/3 to the power of 9, and yep, there I get it again, 3.048315806 E negative 4. Well, that's a really, really tiny number. That's what that means. It's a super tiny number, but what actually is that number? Well, I'm going to hit Math Frac. And if you're lucky, if your calculator is one of the newest models, then your calculator will math frac this weird decimal. And your calculator will say unto you, the answer is 2 over 6,561. That is the fractional answer for number 10, or for the 10th term. Now hold on a second. This is where geometric stuff can get a little bit trickier than arithmetic stuff, because sometimes our calculators overload and they cannot convert the answer back into a fraction. I call that calc overload. Now the thing is, there's a way around it. There's a way to get around it. So let me just show you. If your calculator gives you one of these weird super decimals and you go to math frac, remember, under the math menu on your calculator, one of your choices is frac, and it's supposed to take your answer and change it into a fraction. If it won't do that, that just means you got to be smarter than a calculator. And here's how you do it. I want to know the 10th number in the list. So I go 6 times 1/3 to the 9th. Yeah, I know, we just did this. Here's where I'm going with this. Your calculator tries to do it all at once, but you can separate it mentally. Look, 1/3 to the 9th means the top number to the 9th power and the bottom number to the 9th power. Well, what does that mean? Well, let's continue. It means 6 times 1 to the 9th over 3 to the 9th. That's what it means. Now, my calculator can easily do 1 to the 9th. It's going to get 1. So I'm going to write my result down here. I'm going to give myself some room. And I'm going to say, this means 6 times 1 over... Now, 3 to the 9th, my calculator can actually do. 3 to the 9th, it's 19,683. Which would make my answer 6 over 19,683. But that's not the answer my calculator gave me. Well, that's because your calculator said, hey, don't forget, this number right here, this 6, 3 goes into 6 twice. 3 goes into this. Well, you can do it on your calculator if you want, but I'll tell you, 3 goes into that 6,561 times. So, what I just showed you is a trick you can use in case your calculator overloads and will not allow you to use the math frac feature on it. Remember, calculators can't do everything. They do a lot of awesome stuff, but they do not know how to think. Alrighty, so when you guys are working through this lesson, you are going to run into different, sequences, and I'll say write the recursive definition or write the rule or something. So let's just practice a couple random ones. So let's suppose, for example, I give you something like this, and I say, given, that's something they do in math a lot, given a1 equals 4, and a sub n equals a sub n minus 1 times 2/5. What did they just give me? What did they just give me here? What is this thing called? That's called a recursive definition. So they might say, given this information, what, and I'm going to do this to you on the assignment, what are the first 3 terms in the sequence? Well, you already know the first one because it's 4. They told you A1 is 4. But how do I get the next one? Well, remember, if you want to know the next number in the list, as long as you know the one that came before it, multiply it by 2/5. So you already know it starts at 4. So 4 times 2/5, well, that's 8/5. Well, what about 8/5 times 2/5? I'd get 16/25. And that, my friends, would be the first 3 numbers in the sequence. Sometimes they'll do something like that. Or sometimes they'll give me something like this. They will say, given a sub n equals 5 times negative 3 to the n minus 1. What are the first 3 numbers of the first three terms in the sequence. Well, now I look at it and I go, well, wait a minute. They didn't give me a recursive definition. They gave me an nth term definition. Or think about it. What are the other ways they call this? An nth term, or they call it a rule. Now, it's not the rule writing formula because they already filled in the blanks for you. So it is a formal rule. But if you understand what you're looking at, first number is 5, because in the rule formula, remember, we write a sub n equals a1 times r to the n minus 1. So that guy right there, that must be a1. And this must be r. So the next number in the list is not -3. No, that's not what that means. It means the next number would be -3 times that number. What? Yeah. And then what's -3 times that? It would be 45. And then if I wanted more, I would give you more. But stop, put on the brakes. They only want the first three terms. Now, some people say, I didn't do it that quick. Slow down. Well, let me say it this way. If you need to know the first three numbers in a list, it's as easy as n equal 1, 2, and 3. N equal 1, 2, 3. Look, if I plug in 1 here, that means I'm putting a 1 here. 1 minus 1 is 0. Anything to the power of 0 is 1. 1 times 5. That's why this is a1. But if I plug in a 2 here, that would mean a 2 here. That would mean I'd have 5 times -3 to the first. Oh, that's 5 times negative. Oh, there it is, you know. So if you have a rule, doesn't matter what it is, a sub n equals 4 times 1/2 to the n minus 1, and I say, what are the first three numbers? If you plug in 1, you will get a1. And what is the first thing that would come out of this? 4. If you plug in 2, that would mean 4 times 1/2 to the 2 minus 1. So 4 times 1/2, that would be 2. And then plug in 3. If you plugged in 3, you would get 4 times 1/2 to the 3 minus 1 is 2. And then you could just say, oh, that's 1. So I could still generate the first three numbers of the list pretty quick. It's a very common thing where they'll give you a rule or a recursive definition and say, can you generate the first three numbers of a list? Or something like, if I give you this list, what is the 10th number in the list? What's a10 equal? Well, I could write out 10 numbers to tell you the answer, or I could say, hey, there's a1. I know that r is a half. Heck, I already have this beautiful rule here. So I could say a10, what does it equal? Well, it equals 4 times 1/2 to the n minus 1. Well, that would be a 9. And then I could just grab my calc, which I'm going to do. And I could say 4 times 1/2 to the power of 9. And I get some ugly megadecimal. But I don't want to leave it that way because I could math frac it. See, a lot of the time in math, people will avoid using fractions just because decimals are usually easier to play with. Not really. Not in this case, because the answer I got when I punched it into the calculator was 0.07812. That's not a very pretty number, but if you convert it to a fraction, it's 1/128, which looks so much more compact. It really does. That's a much more compact answer. So, here's the good news. You guys already went through the arithmetic sequence lesson. And if you already went through the arithmetic sequence lesson, then this lesson, man, it's a lot of the same stuff. But you're dealing with R, not D. In arithmetic land, it's D. In geometric land, it's R. but it's still written very similar. So just to recap here, these were all just little examples I made up to help you practice, but it all boils down to this. This thing right here. This guy is called the nth term, or the nth term definition, or the rule writing formula for a geometric sequence. That's what he's called. He's right there. Then there is the recursive definition. Whoop, I didn't want to do that. I'll back that up. Recursive definition format, it's always this, and you just fill in the blanks, just like you did with arithmetic stuff. And of course, the other way to describe a sequence is to write the list. And remember, this is something you might forget down the road, but when they get gnarly and you're like going, I wonder what the ratio is, just remember the common ratio. Take any number in the list, any number in the list, and divide by the one that came before it. And I know you're not supposed to write like that, but I'm a teacher, so I mean. Anyway, there we go, guys. You ready? Let's take a look at what we have to do. Geometric sequences, Unit 5, Video 2. Here's the practice problems I want you to do. Write a recursive definition, a rule, and find the 7th term for each sequence. So right here, I just said, let's practice the basics. Write a recursive definition, a rule, and find the 7th term. Now, just so you know, in the answer key when you check them, I didn't write any recursive definitions because they're easy to write, and I'm trying to save a little time on this video and not make it super long and all that junk. And you know what? You can always ask me in the Zoom room. I will go through anything you'd like. And then use the rule, second part here. Use the rule to write the first 3 terms of each sequence. Okay, and then here's the part I don't want you to get confused on. Right here where it says write the recursive definition for the problems 9 through 12 above. So 9, 10, 11, 12, I want you to call the answers to 13, 14, 15, and 16 here. You're going to see those are recursive definitions. Those ones I wrote. I wrote some of them. And then here's the second page, or the back side of this worksheet. And I just made up some random questions. If A1 equals 5, A sub n equals A sub n minus 1 times 3, what does A sub 6 equal? Okay, so I just wrote out 4 random questions there. All right? Okay, that's that. Here's the answer key. And like I said, I did not include the recursive definitions for 1 through 8 because I didn't want to. I have that right sometimes. I embrace my right to be lazy at least once in a while. And then this one, number 18, it's kind of hard to read, so it's 32/27. So guys, take a picture of it, and then I'm going to scroll up. Take a picture of it, and then I'm going to scroll up one more time. And take a picture of it. And that is your last part of this lesson. Okay, enjoy your geometric sequences. Bye-bye.